What is an empirical formula? Well, the definition is it is the simplest whole number ratio of atoms in a substance. So for instance, CO2, you have one carbon and you have two oxygen atoms. That's an empirical formula. That's the simplest whole number ratio. The next compound is hydrogen peroxide, H2O2. That is not the simplest whole number ratio of the atoms in hydrogen peroxide. This can be simplified, so its empirical formula is simply just HO. The next one is glucose, C6H12O6. That is not the simplest whole number ratio of the atoms in glucose. It can be simplified even farther, and so the empirical formula dividing everything by 6 would be CH2O. So that's what an empirical formula is. It is the simplest whole number ratio. So if you can simplify those subscripts down at all, and then you should do that when they're asking you for an empirical formula. So what is a molecular formula? Well, the molecular formula is the chemical formula that indicates the actual number of atoms of each element in a molecule of the substance. Sometimes the molecular formula and the empirical formula are the same. So for instance, we saw in that last slide CO2. That is the empirical formula, and it's also the molecular formula. This is benzene, C6H6. That is its molecular formula. It's not the empirical formula because we could simplify it further, and the empirical formula would just be CH. In the hydrogen peroxide that we looked at, H2O2, that's its molecular formula, but not its empirical formula. We could simplify it farther by dividing by 2 and having HO. All right, what we're going to do now is we're going to use percent composition data, and we are going to determine empirical formulas of compounds. If you were in AP chemistry, we would do something called combustion analysis to determine an empirical formula. But for honors and standard chemistry, we're just going to be using percent composition data. All right, so let's just get started. Here's a percent composition problem. Mercury forms a compound with chlorine. Determine the empirical formula if the compound contains 73.9% mercury. It doesn't tell us how much chlorine it contains, but there's only 2 elements and it would have to add up to 100%. So to get the percent that is chlorine, we're going to have to subtract the 73.9% from 100, and that gives us 26.1% chlorine. Okay, now that we have the percent composition of this compound with mercury and chlorine, let's get started. Well, the first thing we do is let's assume we have 100 grams of compound. When we do that, then those percentages just becomes grams. If we had 100 grams of a compound and 73.9% of it was mercury, then in 100 grams, 73.9 grams of it would have been mercury. And then that remaining 26.1%, if we had a 100 gram sample, 26.1% would become 26.1 grams of chlorine. So you just change that percentage sign into grams and you're good to go. Step 1, you convert percentages into grams. Step 2, convert grams into moles. And we're going to do that by dividing by the molar mass. And so we're going to use the periodic table, and a mole of mercury has a mass of 200.59 grams, and a mole of chlorine has a mass of 35.45 grams. So we're using all those skills that we learned in those previous videos. We're converting grams to moles. So 73.9 divided by 200.59 gives us 0.368 moles of mercury. Dividing 26.1 by the molar mass of chlorine, 35.45, is going to give us 0.736 moles of chlorine. Okay, so step 2 was converting the grams to moles. Step 3, well, let's go ahead and write down the moles that we just calculated. For mercury, we had 0.368 moles, and for chlorine we had 0.736 moles. All right, what we're going to do is we're going to divide all the moles by the smallest number of moles, and that's going to give us the mole ratio. So which number is smaller, 0.368 or 0.736? The answer is 0.368, and so we are going to divide both of these by 0.368. And this gives us a 1, and this gives us a 2. And so it's a 1 to 2 ratio of mercury to chlorine. So if you didn't get that nice whole number like we just had for the mercury and chlorine, you would need to multiply these terms by integers that would give you a whole number. But that wasn't necessary in this problem. All right, we'll do an example where it is. Our empirical formula is 1 mercury with 2 chlorines. We would name it mercury 2 chloride. All right, let's do another problem. This one has 3 elements. It's vitamin C, and we have 40.91% carbon, 4.59% hydrogen, and 54.50% oxygen, and they'd like to know its empirical formula. So we're going to assume 100 grams of the compound, and so that would give us 40.91 grams of carbon, 4.59 grams of hydrogen, and 54.50 grams of oxygen. So again, step 1, change that percent sign into grams. Step 2, convert our grams to moles. And we do that by dividing by the molar mass. And so 1 mole of carbon has a molar mass of 12.01 grams, and 1 mole of hydrogen has a molar mass of 1.01 grams, and 1 mole of oxygen has a mass of 16 grams. So when we do that, we've converted all of our grams into moles. We are going to get 3.41 moles of carbon. For hydrogen, we are going to have 4.54 moles of hydrogen. And for our oxygen, we're going to have 3.41 moles of oxygen. Okay, so step 1 was to assume we had 100 grams. We just changed those percentages into grams. Step 2 was converting all the grams into moles. Do you remember step 3? Step 3 is to divide by the smallest number of moles. So again, we had 3.41 moles of carbon, we had 4.54 moles of hydrogen, and 3.41 moles of oxygen. The smallest number in all of these is 3.41, so we divide all of them by that. And this time, we don't get a really nice whole number. You really can't just round that down to 1. We want this to be a whole number, and it really didn't turn out to be 1. So what we need to do is we need to multiply this by an integer until we get a whole number. So that is step 4. Multiply each term by the smallest integer that will produce a whole number ratio. All right, 1.33, if we multiplied it by 2, would give us 2.66. Still not close enough to a whole number. If we multiplied it by 3, we would then get a whole number very close to 4. Now, whatever we do with this element, hydrogen, we multiplied it by 3. We have to do the same for all the other elements. So we have 3 carbons to 4 hydrogens to 3 oxygens. So our empirical formula for vitamin C is 3 carbons to 4 hydrogens to 3 oxygens.